Alright, let's talk about combustion reactions. So combustion is literally just something burning. To date, we've mostly just talked about combustion of hydrocarbons or organic compounds. So that's just a compound that contains carbon, hydrogen, and sometimes oxygen. Now, combustion reactions are really nothing more than a really important redox reaction. What makes them really important is kind of the everyday use. If you think about a combustion reaction in your car, your fuel undergoes a combustion reaction or redox reaction, generates energy that pushes you around. Also, metabolism. Every time you eat something, your body metabolizes sugars, fats, proteins, and it converts them into energy via a combustion reaction or a redox reaction. So if you think about it, when you eat food, so you eat like sugar or something, sugar is just C11H22O11. When you eat that and you breathe in oxygen, your body generates heat energy, and so that's what you use to power you. And then you exhale carbon dioxide, and the H2L, well, I'll let you figure out what you do with that. So the same reaction that you see down here of methane burning, this is what happens every time we use a Bunsen burner in class. The same general reaction that's happening with that Bunsen burner is what's going on in your body. Obviously, you're not setting yourself on fire, you're taking that energy and converting it to other things. Writing these notes, you're burning energy, you're undergoing a redox reaction. So if we assign oxidation numbers to this methane reaction, hydrogen, in this case, it is bonded to a nonmetal, so it's going to be -1. That means carbon is +4. Oxygen here by itself is going to be 0. And carbon dioxide, it's -2, so that means carbon's +4, -2, +1. And so we can see that hydrogen was changed from -1 to +1, which means that it lost electrons. And we can also see that oxygen went from 0 to -2, which means it gained electrons. So that means that oxygen is reduced and hydrogen is oxidized. So combustion does not just have to involve carbon and hydrogen compounds. It can also involve elements. So anytime an element is burned in the presence of oxygen, it's going to generate its oxide, which means combining with its particular oxidation state and oxygen. So for example, sulfur being burned in air. And the way we recognize this as a combustion problem is the key words burned and air. Remember, air is partially oxygen. There's the presence right there of oxygen. So if we burn sulfur and oxygen, oxidation state of oxygen to begin with is 0, of oxygen is 0. Then over here we're going to -2 and +4. So we recognize that +4 is one of the typical oxidation states of sulfur. Another oxidation state of sulfur would be +6, in which case it would generate SO3. And actually either one of those would be acceptable answers for that question right there. Same thing with calcium oxide. Calcium 0, oxygen 0, and then it's going to -2 +2. In this case, calcium is oxidized, oxygen is reduced. Same thing with the sulfur oxygen one. And how I got calcium oxide for this one should be a little bit easier because calcium forms an ion with +2, oxygen -2. So those are the only possible oxidation states for those.